From groundbreaking research to the conversations shaping the future of AI. This is Jekaterina, covering the ICLR 2026 Conference for Women in AI Research.
Could you please introduce yourself?
Hi, I'm Nikita. I'm a fifth-year PhD student at the University of Toronto and Vector Institute. And I'm presenting my work here at ICLR at a workshop on approximating function space distances for continual learning and transformers.
Amazing. Could you walk me through this?
Yes, definitely. So the goal of this work is to estimate what we're calling a function space distance. This is motivated by several applications. The main one we experiment with is continual learning. But essentially here, imagine you train some network to learn parameters, let's say θ0 on data drawn from a distribution P data. And then you want to continually learn some other task, or maybe you have an unlearning task or a model editing task, in all of which there's this requirement to preserve predictions and performance on the previously seen data, which was P data in our case. So to formalize that, you want to maintain predictions while training θ1 on data that came from P data. And θ0 is a network that was originally trained on P data. And the reason we might want this function space distance is to prevent something like catastrophic forgetting. So if we can measure the distance in output space, so let's say the neural network is denoted by F in output space, so we can measure this distance between θ1 and θ0 on predictions with input X, where X is drawn from P data, then we can use that as a regularizer, prevent catastrophic forgetting, maintain the predictions we're interested in. And the main goal for our paper is to try and do this efficiently under the constraints that we don't have access to individual data points from this data distribution, but we can assume access to statistics. So the first two moments of the data distribution, where the first two moments come from is if you have the Euclidean distance that you're interested in here, the Euclidean distance can basically be written in terms of the first two moments of this delta F. And if I can measure the first two moments of the output space difference, then I can essentially use that as a regularizer. To get these first two moments, so we can just think about the first moment, and then the same logic applies to the second moment. To get this, what we do is make two approximations to every step in our forward pass, such that we can basically propagate the moments through the network. So I can take the first two moments of the input data, propagate it through the network to get the first two moments of the outputs. And if I can do that, then without using any individual data points, I have the function space.
And it's just 2 moments because it's linear.
Because we make a linearization approximation. So it's not necessarily linear. We make a linearization approximation and one independence approximation. And then we empirically verify how bad those approximations are and how much error we incur. And sort of the punchline is that it's not too bad. And if we do that in a fine-grained manner, we can get very good performance. So you already preempted sort of what the assumptions are going to be. One is I want deltas. So let's say this is one step of the forward pass. Take some inputs, these, some parameters, pass it through some nonlinear function, and you get some y. What I'm interested in is delta y's, like y1 minus y0. So the linearization here is going to be just the first order Taylor approximation. It's going to depend on some Jacobian with respect to the input, some Jacobian with respect to the theta. But remember I said I don't just want the deltas. I want the expectation of the deltas or the moments of the deltas. So that's where the second approximation comes in. I want this expectation. I make an independence assumption here to basically push through expectations here. So that now I have this expected Jacobian, expected delta, and then again, expected Jacobian, expected delta. This is essentially what we're calling an expected Jacobian vector product. So what I really need here is enough information stored so that I can compute that expected Jacobian vector product. And turns out with some approximations, maybe diagonal approximations, you can do that fairly efficiently. Which sort of is easier to explain in our code base how to do that in a modular fashion, but you can do it and it works. And the sense of this picture basically shows the same thing. You have some step in your forward pass, you make a linearization assumption, you want the deltas again under linearization, and then you make an independence assumption to get from your first two moments of the input to the first two moments of the output. And if I do this for every step of the forward pass, I eventually go from the first two moments of X to the first two moments of the outputs, which is what I want. That's the whole sort of summary of the method. The way we evaluated this was in a somewhat synthetic task with transformers. We want to see if we can do this with transformers. So we had a modular arithmetic task where we learn addition, modular some number, 113, and then sequentially learn subtraction. And the goal is to prevent catastrophic forgetting on the addition task because we've lost access to that data now. And so this is the main summary of the results and then some ablations and analyses. This is the Oracle method where we assume access to all the data points that we have. So you can sort of compute this with a Monte Carlo estimate. If you have access to X's here, sample many X's, compute this. So if we could do that, then we get this performance where your average accuracy across tasks is really high. Your average backward transfer, which is a measure of forgetting, and higher is better, is also really good. Over here, our method, which we call lifter, because it's a linearized function TRick, gets pretty close, at least some versions of it get pretty close to the Oracle, which is nice. Just to explain a little bit the different versions, we have a deterministic version where the expectation over here is this is a deterministic computation. And then we have a stochastic version where we can give certain distributions to that, to this Jacobian and this computation, and then draw samples from that distribution using the statistics again. So again, not using any real data points, but just imposing a distribution. Turns out the stochastic version tends to work better. This might be because continual learning benefits from stochasticity to some extent. And then the other versions here, wherever you see diag, is we've made diagonal approximations wherever we have a large covariance matrix. That's really expensive to make a diagonal approximation. And that doesn't really harm performance all that much in the stochastic version.
Say that, okay, these two are both stochastic.
And that's deterministic. And this each has a non-diagonal and a diagonal version.
The differences in accuracy are not that big compared
with the diagonal. Yes, that's true. So there is a bit of a trade-off here that's controlled by this hyperparameter. So this lambda controls how much I'm regularizing my FSD. If this is really high, I can basically prevent all forgetting and get really good backward transfer. If this is really low, then I can get really high accuracy on my second task, which is going to push up the accuracy here. So, which is why, that's a really good question, which is why instead of just reporting numbers, what's more useful to look at are Pareto fronts. So this is task 0 versus task 1 accuracy if you have 2 tasks, and every point here is a different lambda. So as I increase the lambda, I'm increasing my function space distance regularization, so I should do better on task 0. And as I decrease lambda, I should do better on task 1. And your best performing method would be the one that has the highest area under this curve. So you can see the Oracle is like all the way at the edge. No matter what the lambda is, or with all lambdas, you sort of get pretty good trade-offs. Our methods, or at least the lifter S methods, are the ones that still do better across all hyperparameters here because they're the closest to the Oracle.
And the diagonal
gets actually quite a bit worse. And my suspicion is that that's because continual learning just benefits from stochasticity in general. But there might be other tasks that would benefit from deterministic approximations. So yeah, and then I guess the other couple of analyses that we did are to see why this works well. So one thing we looked at was how well our estimated function space distances correlated with the Oracle function space distance. We get good correlations, but some of the other baselines also get correlations in spite of having poor performance here. So we realized that maybe a more useful metric to look at is actually the gradients produced by these computations, because really what I'm going to do is I'm going to regularize this quantity with gradient descent or some optimization technique. So we looked at the gradient cosine similarity between our function space distances or the baseline function space distances and the Oracle function space distance. And here it's much more clear that for our method, which are the lifter methods, you get higher gradient cosine similarity across training than the baselines, which have much lower gradient cosine similarity, which sort of explains why you would see worse performance for it.
And I expect your method diagonal will be somewhere in between, probably, right?
Yes. So diagonal's actually pretty close. Green and yellow are both the stochastic version. Green is diagonal and yellow is not diagonal.
Okay.
I didn't show the deterministic version here to avoid clutter, but the deterministic version somewhere in the middle. Yeah. And then finally, the last bit of analysis is on the effect of depth on linearization, because here, notice we're doing this approximation for every step of the forward pass. So you can imagine as I have more steps in the forward pass or a deeper network or more number of blocks in my transformer, you would have, you would accumulate more errors. And so that's why we wanted to look at it. As I increase the number of blocks, we went up to 8 over here. How does my accuracy and backward transfer change? And for the lifter methods, so sort of the oracle stays really high throughout because it doesn't depend on depth. There's no approximation there. Lifter does drop all the way at the end when you have 8 blocks, but it's sort of a graceful decline. And our main baseline, which was another kind of linearization, which I can explain, that has a much sharper drop. This baseline is because we're making linearization approximations, we decided to compare against global parameter space linearization, that's commonly known as NTK regime. And that is actually a fairly strong baseline. Its performance is not that much worse. It's worse, but it's not that much worse. But it does suffer a lot more from greater depth because you increase the depth, the linearization is much worse if you're doing it globally. We don't suffer as much because we're doing layer-wise linearizations. We're doing a more fine-grained computation, so you don't suffer as much. Yeah, I think that's all our summary. That's the entire summary of the work.
Amazing.
Questions?
Do you think there are, can you think of any limitations to the data that was be important?
Yeah. So one thing is we're summarizing the entire data set in its first 2 moments. It might be more useful to then cluster your data set, maybe in terms of classes, if you have different classes, or maybe some other clusters, whatever the domain specific case is, because maybe the summary in terms of moments would be better, would better summarize the data set if you just clustered it. So that's possible. And that's some previous work that this is actually a follow-up on a previous paper of mine, and that we actually did explore class conditional estimates. So that could be more useful. That becomes more computationally expensive and also more memory expensive. You would then have to store many more things. The other thing that's kind of a limitation that is a little unsatisfactory right now is that we make these, assumptions on like independence. So we make this linearization approximation. And I think the results sort of indicate that layer-wise linearization doesn't change too much. Like that approximation is not that bad. So maybe as we're continually training, we're roughly linear. That's why our approximation didn't hurt as much. This one's less intuitive. So I think this independence assumption that the Jacobian and the delta of the inputs to your function are independent. It does seem that it doesn't hurt our performance as much, though we should test this at scale. But like, yeah, I think this is less intuitive. This could use more analysis to sort of understand why we can do this or in what settings we can do this.
Right.
Yeah.
How would you explain that the variance of your variance here is even smaller than the variance of Oracle?
Oh, that is true. So I guess, So I think with the diagonal version, it's not that much significantly smaller, but yeah, I do see all of the fur is smaller. With the Oracle, it is a Monte Carlo estimate. So I think this would go down as I increase the number of examples.
Right.
So yeah, that's probably the case that at some number of examples, this can go down. Here, there is no notion of data points. So deterministic is already just like that. There's very little stochasticity. So that should be lower. Here also, there is very little stochasticity in terms of data points. You already summarized in the first 2 moments. So that would be my guess that if I increase the number of data points for the Oracle, this would go further down. Yeah.
I see. Yeah, that's super interesting. Thank you.
Thank you so much for stopping.